Hi, my name is Reddy, and I'd like to present our recent work on assisted perception, optimizing observations to communicate state. The goal of this project is to help users estimate the state of the world in sequential decision-making tasks like robotic teleoperation and navigation with visual impairments. Consider a visually impaired user trying to navigate a house. They can't directly perceive the scene in front of them. Looking at the house from a bird's eye view, they're trying to reach a position in the middle. They think they're in one corner of the house, but in reality they're actually in a different corner. This mistake in state estimation can cause the user to move farther away from the goal instead of toward it. So what exactly went wrong with the user state estimation process? Typically, the user would receive the full image observation, then think to themselves, given the observation I just received and the action I just took, I'm probably now at the following state. This state estimation process takes a history of observations and actions and maps it to a belief distribution over possible current states. After updating their beliefs, the user then takes an action that makes sense to them given where they think they are, for example, turning and walking toward their goal. The problem is that the user may have perception difficulties or systematic biases that prevent them from making use of that full observation, which in turn prevents them from accurately estimating the state and then taking an optimal action for their desired task. Users can have trouble processing observations for a variety of reasons, like not being able to pay attention to many different sensors at the same time, or lens distortions causing them to overestimate distances to objects, or even optical illusions affecting the user's biological vision system. The roller illusion you see here seems to be animated, but it's actually just a static image. The key insight in this work is that true, full observations are not necessarily the most informative about the state, especially when they're processed incorrectly by the user due to systematic biases in perception. We operationalize this insight by using an automated assistant to process the full observation on behalf of the user. This assistant performs state estimation unencumbered by systematic biases or perception difficulties that the user may have. Then the assistant provides the user with a different, modified observation that is more accessible to the user than the full observation. The user then takes this modified observation and performs state estimation using their potentially suboptimal process. We call this method assistive state estimation, or ACE. The ultimate goal of ACE is to make the user's belief match their true state. One challenge with this approach, though, is that the assistant doesn't necessarily know the true state, so we settle instead for trying to make the user's beliefs match the assistant's beliefs. Formally, we try to minimize the KL divergence between the assistant's beliefs and the user's beliefs. After the assistant processes the true observations, it synthesizes a modified observation that it thinks will make the user believe in the same state as the assistant. The main challenge with this approach is that we don't have access to the user's internal state estimation process. We address this problem by learning a model of the user's belief update from demonstrations of user actions. We start with an initial model of the user's state estimation process that makes some assumptions about the user's systematic biases and perception difficulties. We then use this initial model to assist the user and record the actions that were taken by the user while they were being assisted. Because the initial model may not be accurate, even with assistance, the user may still take suboptimal actions. Then, after the episodes are completed, we ask the user which tasks they were trying to perform in those episodes. For example, we ask them which goal states they were trying to reach. This enables us to compute the optimal policy for the tasks, and then to fit a new user model that explains the gap between the optimal policy and the user's suboptimal actions. Specifically, we train the user model to explain the actions the user took. We model the likelihood of the user taking a particular action, given a history of observations and past actions, by marginalizing out the state. This involves computing a near optimal policy for the completed task, and representing the user's beliefs using a parametric model, for example, a neural network. We train our model of the user's state estimation process using a maximum likelihood objective over the demonstrations. In our experiments, we consider two types of tasks: tasks in which we assume prior knowledge about how the user's state estimation process is flawed, and other tasks in which we don't know the user's biases upfront and need to learn a model instead. We look at MNIST and car racing game domains in which the user's perception is bandwidth constrained, or subject to intermittent delays in the arrival of new observations. We also look at a lunar lander game in which we might expect the user to consistently underestimate certain state variables, but we aren't quite sure about when or to what degree this actually occurs. In the first set of experiments, we assume the user is primarily affected by limited sensor bandwidth. Consider the navigation with visual impairment setting described earlier. The assistant might detect many different objects in the scene, but if the assistant were to simply tell the user about all of them, the user would be overwhelmed and may not be able to incorporate the new information and move toward their target. A simple initial solution to this problem is to inform the user about just one of the visible objects selected uniformly at random at each time step. The problem with this method is that it may end up providing the user with uninformative observations about common objects that happen to be found throughout the house, and hence do not help the user figure out where they're standing. So while the user does get some information, they may still be unable to make good decisions. Our method optimizes the assistant's choice of which object to inform the user about at each time step. By telling the user about landmark objects that can only be seen from the user's current position, the assistant induces more accurate beliefs in the user, which then leads to more optimal user actions. We ran experiments with simulated users navigating a simulated indoor environment. The guide can see the user's egocentric scene, but the user cannot. The guide can also determine which objects are present in the scene, and in the baseline condition simply selects one of them uniformly at random to tell the user about. The user receives this categorical observation of an object from the guide, then looks up all known locations of that object throughout the house in their mental map of the house. The user then updates their beliefs about their current position and orientation and attempts to move along the shortest path to the goal. Our method improves upon the default guide by optimizing the choice of object information to give the user. This tends to result in more accurate user beliefs and, as a result, the user taking less time to reach their goal. Thanks for listening. You can read the full paper, watch more videos, and access our code from the project website.